Carbocation rearrangement. It is a rearrangement of a less stable to a more stable carbocation by a shift of a hydrogen or a shift of an alkyl group. When the shift is between hydrogen, it is 1,2 hydride shift or 1,2 H shift. If the shift is involving alkyl group, we call it 1,2 methanide shift. 1,2 means at carbon 1 and carbon 2. So that is the position of the hydride and methanide. For example, here, 1,2 shift, this R can be CH3, can be alkyl group, can be methane. If it is methane, we call it methanide shift. If it is hydrogen, we'll call it hydride shift. So this 1,2 means at carbon 1 and carbon 2, the carbon must be neighboring carbon. So the shift is alkyl or hydrogen, methanide or hydride from this one carbon, shift to the other carbon, and the position of the carbocation is also changed because this carbon, the carbon here initially has 8 electrons, octet, but when it shifts the hydride or methanide, it has less than 8 electrons, so the position of carbocation also change. So this is what we call 1,2 shift, hydride or methanide. Here is an example of secondary carbocation. This carbon attached to 2 other carbon atoms, so we call it secondary carbocation. And the hydrogen at the carbon here means hydrogen attached to the carbon neighboring carbocation. So this hydrogen shift the position at the carbocation carbon, so we call it as 1,2 hydride shift. So the carbocation position change and the hydride change the position. So now this carbon becomes a carbocation and this carbon is tertiary carbon. The carbocation rearrangement happens if we want the carbocation to be more stable. Initially, this is secondary carbocation, and at the product, it is tertiary carbocation. Tertiary carbocation is more stable than secondary carbocation. So that's why we did the 1,2 hydride shift. Same goes for this one. If you focus on this carbocation, this is secondary carbocation because 2 alkyl group attached to this carbon, 2 carbon attached to this carbon, so this is secondary carbocation. If we do the 1,2 methanide shift, this methanide position shift to this at the carbocation position, and the carbocation position shift to this position, it becomes the tertiary carbocation. So tertiary carbocation is more stable than secondary carbocation. So we have to do this 1,2 methanide shift to achieve the more stable carbocation. Here, in the dehydration of alcohol, remove the OH group from this carbon, and you can remove the hydrogen atom from this carbon, and no hydrogen can be removed from this carbon here. So we did the carbocation shift or 1,2 methanide shift because there's no hydrogen here. So if we remove the OH group from this carbon will become carbocation. So if you do the methanide shift, this CH3 shift to this carbon, making this carbon tertiary carbocation. If the carbocation maintained at this position, the carbocation will be secondary carbocation. Methanide shift here, tertiary carbocation. So this is more stable the major product will be this one. The removal of OH group here, but after 1,2 meta-night shift, you can form major product with more stable alkene, highly substituted alkene, 1, 2, 3, 4 alkyl group attached to this carbon-carbon double bond. And if you do the meta-night shift, the carbocation will be here. The carbon-carbon double bond form can also be here. So this is the minor product, two minor products of the dehydration of alcohol and one major product of dehydration of alcohol. Okay, step number 1. This OH group, the electron-rich oxygen, use 2 of its lone pair electron, 2 electrons from one lone pair of the oxygen, to form bond with the hydrogen. This hydrogen is electrophilic site. The electron poor site form bond, so the bonding electron here, both electron transferred to oxygen of H2SO4, making the product HSO4 minus. The minus is at oxygen because both 2 electrons transferred to the oxygen, making the oxygen has lone pairs. And then when the H form bond with oxygen here, this is protonated of alcohol. Okay, this is the product. And then when the water is removed during step 2, when the water is removed, because this oxygen is positive, oxygen does not prefer to be positive, so that's why it used the electron bond here, 2 electrons between CO bond used to be transferred to this oxygen here, making this oxygen has 2 lone pairs again. So 2 lone pairs again, so removal of water, and then making this carbon as carbocation because it loses the sharing electron here, so this carbon will become carbocation. And this carbocation is secondary carbocation. If we do 1,2 meta-night shift, this carbon will become the carbocation, and this carbon here will attach to the methane. So it becomes the tertiary carbocation. So this is more stable than secondary carbocation. That's why you have to do 1,2 meta-night shift before proceed with the mechanism. Okay, and then step number 3, this is the tertiary carbocation. The HSO4 minus oxygen part, the oxygen side, because it is electron-rich side, will form bond with the hydrogen of the neighboring carbocation. So this is neighboring carbocation, neighboring carbon of carbocation. Oxygen form bond with the hydrogen here, and then the sharing electrons here, those 2 electrons will be used to form double bond between these 2 carbon, because the carbon here is electron poor, carbocation electron poor, so these 2 electrons used to form double bond between these 2 carbon. So since this is the tertiary carbocation, this is the major product. And when this oxygen form bond with this hydrogen, it will become H2SO4 again, and alkene. And then here, if the HSO4 negative form bond with the hydrogen of another carbon, okay, initially this hydrogen from this carbon, and then it will attack this hydrogen here. This carbon is still the neighboring carbon of carbocation, because this carbon beside this carbocation, this carbon is beside this carbon, beside this carbocation as well. So HSO4 minus can attack any hydrogen which is beside the carbocation. So it can attack hydrogen from this carbon, it can attack hydrogen from this carbon, and it can attack the hydrogen from this carbon as well. This step, it shows when the HSO4- attack the hydrogen from the neighboring carbon on the left. When it attack here, making this electron between this bond, this electron form the double bond between these two carbon, and if you count, this has two alkyl group only. Focus on the carbon-carbon double bond, it has 1, 2 alkyl groups only. But here, focus on carbon-carbon double bond, it has 1, 2, 3, 4 alkyl groups. So that's why this is the major product, this is minor product. Less alkyl group, minor product. More alkyl group, major product. Step number 3 is when this carbocation maintain the secondary carbocation. If you don't do the meta-night shift, if it is maintained as secondary carbocation, the HSO4- will attack the hydrogen of the neighboring carbon. So here, neighboring carbon of carbocation, and then these two electrons will be used to form bond between these two carbon, and this is also the minor product because it is from the secondary carbocation, less stable carbocation. The product is minor because if you focus on this carbon-carbon double bond, it only has one alkyl group attached to it. So minor product.